evening, everyone. We are in the week 2 problem solving session of the NPTEL course Control Engineering, and week 2 is about Laplace transforms, transfer functions, and block diagram representation. I am Tejo Golla, a fifth year research scholar working under Professor Santanu Kapat at Embedded Power Management Lab, IIT Kharagpur. Let me share my screen. Can you see my screen? Hello. Can anyone please confirm if you can see my screen? Niladri, Saurabh, are you there? Yes. Okay. Good evening, Saurabh. Okay. So I hope you have gone through the lecture videos of week 2. Week 2 is about Laplace transform as well as transfer functions and block diagram representation. So I'll be giving a very quick good evening, Niladri. I'll be giving very quick summary of Laplace transform, why we will be using Laplace transform, and then we'll dive into few properties of Laplace transform, and we'll solve more number of problems because we have to be comfortable with Laplace, and that is the only way, which is by solving maximum number of problems. We'll also solve inverse Laplace transform. We'll see how we can apply inverse Laplace transform, and we'll also look into the transfer functions, what are transfer functions, uh, how we can use transfer functions in solving problems, and also what is block diagram representation, because whenever we discuss about control engineering, we always deal with blocks. So we'll see what is block diagram representation, and then that will be used in the upcoming weeks. So we'll be learning that as well. Yeah, Sunny, good evening. Good evening, everyone. I hope all of you have done well in assignment one. If you face any difficulties, please let me know. And I hope these lectures are also helping you in understanding the concepts better, solving your queries, as well as getting some hands-on experience with few problems. So I'll quickly summarize the Laplace transform. So why is Laplace transform needed? Because it is in S domain. So basically, Laplace transform, or whatever we are going to do, or whatever we'll be learning in this course, there are two types of domains. One is the time domain, and other one is the frequency domain. So time domain. So anything that is written in time domain t, and then we also have frequency domain, which is S, which is equal to sigma. It has a real part as well as the omega part. So both of them have their advantages and disadvantages, but whenever it comes to solving the problems, time domain can be difficult to solve the linear differential equations. Also, it becomes very complex expressions when you deal with the time domain. So in this case, it becomes relatively simpler because all our differential equation will become algebraic equations. So it is relatively easier to solve. So that's why we sometimes use frequency domain to solve the problems in an easier way. And also there are many aspects like we can check the stability of the system in frequency domain. So there are certain ways which we can also do in time domain. So in this course, we'll be learning both time domain as well as frequency domain, and we'll try to correlate both. And frequency domain is much easier to deal with compared to time domain, and we'll also see why it is easier. So before we go into the Laplace transform, what is Laplace transform? I'll quickly consider one example, which is also what Sir has considered. So if we consider a spring mass damper, we'll have one second order equation as we have discussed in the last class, which is mx double dot plus bx dot plus, where x dot is the displacement and m is the mass, b is the damping, and dx, sorry, kx, k is the spring coefficient equals to 0. So if you solve this expression, we'll get x in terms of exponential. We can say e to the power minus at into some constant a into sine omega t plus theta. So if you solve by time domain, you need to deal with both the exponential term as well as the trigonometric term. So as you can see, this is the exponential term. Exponential term. And this is the trigonometry term. Or I would say sinusoid instead of trigonometry, exponential as well as sinusoid term. So whenever we are solving in time domain, what are we basically doing? We are trying to solve this differential equation and we'll be integrating it and then get the solution, right? So this is basically the solution that we are talking about. So this is the solution. If we calculate by time domain, we have to deal with both the exponential term as well as sine term. So in that case, what happens? uh, the integration that we have to do to get the solution will make our lives much more difficult because we need to deal with these two terms. So is there any possibility to separate both the terms? So if you ask this question, can we separate these two terms? Can we separate these two terms? Yes, we can separate, and by using Laplace transform. So we apply the Laplace transform to the given equation, solve it, and then apply inverse Laplace transform. But what are we benefiting? What are the benefits that we are getting? We'll try to separate the exponential term as well as sinusoid term so that it will becomes easier to solve the problem, and then we'll apply inverse Laplace transform to get the time domain solution. So basically, we'll apply a transform. And that is basically the today's discussion. Laplace. So this is the motivation for using the Laplace transform. And before we go to the properties of Laplace transform, I'll just quickly define what is Laplace transform. So always time domain. So time domain expression, say we are writing f of s. So we'll usually be writing in small terms. So we'll write f of t, x of t, u of t, y of t, whatever variables we'll be using in small case, not the capital. So after applying the Laplace domain, sorry, after applying the Laplace transform, whatever we'll have in the frequency domain, we use capital letters. Frequency domain, we'll be using the capital letters like f of s, x of s. So now it is in frequency domain, so it's a function of s, u of s, and y of s. So we use capital letters. So this is what everyone follows universally. So not just in this course, any course, after applying the Laplace transform to the given input, the variable has to be considered in capital letters. You cannot consider small letters. So this is the nomenclature that everyone follows universally, and it is accepted. So we also have to stick to the same. Just like how V is considered as voltage, I is considered as current, this is also in the similar way. So we also have to follow the same nomenclature. So now if we consider the Laplace expression, so Laplace is denoted by L. So L of say function f of t. So Laplace of f of t is f of s, is integral 0 to infinite f of t e to the power minus st dt. So this is the expression for Laplace. So why starting from 0? We assume that the input is applied at t equals to 0. So we assume that f of t is equals to 0 for all t less than 0. So we are assuming as far as this course is concerned. So there are like people who consider Laplace from minus infinity to infinity, but in this course, as far as this course is concerned, the inputs that we'll be considering are applied at t equals to 0. So the input is 0 when t is less than 0. So that's why the integral is applied from 0 to infinite and not from minus infinite to infinite. So if you want to find Laplace for any function, we can solve the integral and then we can get the this expression. Is this clear until this point, everyone? Any doubts until this point?
Sir, can I ask one doubt?
Yes, yes.
Sir, actually, what does it mean, sir? Like if we are integrating from 0 to infinity, a function
Yes, yes,
multiplied by an exponential function e power minus st,
yes.
what does it physically mean?
So it is actually, what do you say? It's a transformation. Like we are converting one domain, time domain to a frequency domain. So you are converting some rupees to say dollars. There is a scalar product, right? You are multiplying, say $1 is 91 rupees. So you are converting the dollar to rupees. So you are transforming one currency to another currency. There is a scaling. So now if you convert from like a different currency to different currency, the scaling varies. Similarly, when you're changing something from what do you say, this time domain to frequency domain, there is a transformation that we have to apply to get into the S domain. So whatever time domain expression that we have, that we are representing as f of t, and if we apply the Laplace, which is this integral 0 to infinite into e to the power e to the power minus st, then we'll get into the frequency domain.
Yeah, but why till infinite? What does it mean, sir? Integration from 0 to
So
infinite means?
actually, we are integrating that function t from 0 to infinite, and then we are converting it into the frequency domain, which is the S domain. So this is the transformation, and that's how it is defined. Like there is no proof as such. This is the transformation that Laplace has considered and converted into S domain, and have seen how it is benefiting in solving the problems. And
Okay,
then we are using that Laplace transform by convert like using that Laplace transform, we are converting into frequency domain. Like this is how the transform is defined. Like if you see Fourier transform, it has a certain transform equation, right? So using that equation, we'll convert into Fourier. And similarly, we have inverse transform to convert back into time. And then we'll be converting into the Fourier transform to solve the equations for certain applications. And then we'll convert back into time domain.
okay, okay.
Okay. So now let us consider one quick example to discuss something called region of convergence. So there is something called ROC, which is region of convergence. Because we are integrating something, so the Laplace will exist only if the integral exists. So there will be some range only within which the integral exists. So within that range only the Laplace is applicable. So that range or the condition, whatever we get, will get, that is called region of convergence. So let us quickly take one example. So if you consider f of t to be e to the power minus at. Okay, so now let us consider the Laplace, which is f of s is equals to integral 0 to infinite e to the power minus at into e to the power minus st into dt, which is equal to integral 0 to infinite e to the power minus of s plus a into t dt. So now if I apply it, I'll get 1 by, sorry. So now we are considering e to the power minus x. So we'll get minus of e to the power into. So now if you consider this 1 by s plus a into minus e to the power of minus s plus a, right? Or am I making any mistake? Just a minute, sorry. Yeah. So now if you consider e to the power minus of s plus a, so if I consider this expression, so it is e to the power minus of s plus a into t. So we are considering t to be positive, right? Say t is positive. So now if here if you consider s plus a to be positive, then it will be e to the power minus x. So if e to the power minus x is there, then if we consider t to be infinity, then this will tend to 0 as, sorry, this expression will tend to 0 as t tends to infinite, right? Agree? But what if s plus a is negative? So if s plus a is negative, then we'll have some e to the power positive constant x, and this will tend to infinite as t tends to infinite. So in the second case, we'll not get the integration valid. Integration will tend to infinity. So only in the first case, the integration is valid. So it means s plus a greater than 0. This is our region of convergence. So this is called region of convergence. So what is the region of convergence? Here it is s is greater than minus a. Is this clear? So basically I have skipped one step. What you will get is minus into e to the power minus of s plus a. Integration is from s plus a t minus of s plus a into t. Integration is from 0 to infinite. So for 0 it will be 1, infinite it is 0. So we will get 1 by s plus a. So we are calculating it assuming that e to the power minus of s plus a into infinity is 0, but it will only happen if s plus a is positive. So that condition where the integral exists, that is called region of convergence, and from this equation we are getting s is greater than minus a. So is this clear for everyone until this point? Any doubts? Okay, someone has mentioned in the chat. Clear. Okay. Now we'll see each property of this Laplace transform, and then we'll also be solving few problems on each of this concept and see how we can apply that concept in solving that problem. So proofs will not be discussed in this session because we are using the property to solve the problem rather than proving the property. So I'll just consider the property, I'll define the property, and then I'll use it to solve the problems. Okay. So what is time scaling? So initially, let us assume that we have Laplace. So I'm considering x of t, time domain is x of t, and then it is transformed. We have x of s. So now we have x of at. Then we'll have 1 by mod a into x of s by a. So this is called time scaling. So for x of t, if we have the Laplace transform as x of s, then for x of at, we can say that the Laplace transform is 1 by mod A into x of s by A. So this is not product, this is the Laplace transform. So if we know the result of the first one, we can use that result to calculate the Laplace transform of the second one. So now let me just maintain the color clear so that we can maintain the same color throughout the problem solved. So in this case, we'll be using this property to solve the Laplace transform of this expression. So the first one is e to the power minus t. So there are actually some standard results that we can, maybe I'll just write it here, standard Laplace transforms. Or I'll just write in the same, here I'll make up some space and then I'll write it here itself. Yeah, okay. So standard Laplace transforms. So we have the time domain here. And then we have the frequency domain. So for delta function, delta of t, frequency domain Laplace transform is 1. And for u of t step, say we have step u of t, it is 1 by s. Similarly, for t to the power n, we'll have n factorial by s to the power n plus 1. So these are some standard that we can remember so that it can be used directly in any of the problem. Similarly, for e to the power at, we have 1 by s minus a. Okay. So in the previous problem, whatever we have e to the power minus 80, we have 1 by s plus a. So this is 1 by s minus a. So it's like substituting minus a in the place of a. Now we have cos omega t, which is s by s square plus omega square. Similarly, we have sin omega t, which is omega by s square plus omega square. So is this fine? Just some standard results that I'm mentioning so that you can use it. So now coming to e to the power minus t. So we know that for e to the power t, Laplace is 1 by s minus 1. Right? So now we are multiplying t by a constant a, which is minus 1. So now I'll substitute 1 by mod minus 1 into x of s by a. Or you can also use this expression, which is e to the power at 1 by s minus a. So basically e to the power t, it is 1 by s minus 1. So e to the power minus t, what we will be getting? 1 by s plus 1. Now if we solve problem number b, we have sin 2t. So for sin t, what is the expression? Omega equals to 1, it will be 1 by s square plus 1. Okay, I think I'll use the same color else there will be confusion between the transform. Okay. So now sin 2t, one by 2 into 1 by s by 2 whole square plus 1, which is half into 4 by s square plus 4, which is 2 by s square plus 4. So we have used the scaling, time scaling property of the Laplace transform to solve these problems. Is this clear until this point? Yes. Okay. So if this property is clear, then I'll move to the other property, which is time shifting. So basically now time scaling is done. Now we are dealing with time shifting. So everyone said SL. So which is time shifting. We have x of t and we have x of s. Time shifting is t minus some t naught. X of t minus t naught. Then we'll have e to the power minus st naught into x of s. So if we are doing time shifting, then it will be e to the power minus st naught into x of s. So for the first question, A part. So for t into u of t, what will be the Laplace transform? Anyone? U of t means basically t only, but u of t is 0 before time t equals to 0 and u of t is 1, which means our function is t and it starts from t equals to 0. So now if you go back to this table, from here, can you tell me what is the Laplace transform of t? Anyone? What is the Laplace transform of t? Okay, someone has mentioned
1
1 by
upon
s
s
square.
square.
Yes, very good. 1 by s square. So now the Laplace transform of t into u of t is 1 upon s square. Very good. Now what will be the Laplace transform of t minus 3 into u of t minus 3? Anyone? Based on the previous above result. So all of you can try because what else can go wrong? You might be wrong. Then I'll correct you. But if you keep quiet, then it will not benefit you in any way. You should also solve these problems along with me.
E raised to minus 3s into 1
Into
upon s.
s square, right? Yes. Very good. So here our t naught is 3. So we'll have e to the power minus s t naught. So e to the power minus 3s into x of s, which is 1 by s square. So if you solve, this is what we'll be getting e to the power minus 3s into 1 by s square. Similarly, for b, if we solve, what is the Laplace transform of sine t? Anyone?
1 upon s square plus 1.
Very good. 1 upon s square plus 1. So all these basic Laplace transform should be very handy with you. You should remember them. So now using the basic Laplace transform expressions plus these properties, you can solve the questions. Else it will be very difficult. One way is to do the integration, but it is very lengthy. So instead of that, we'll use these properties. So now sine of t minus 2. So what will be the Laplace transform of this?
E raised to minus 2s into 1 upon s. S minus 1 upon S square plus 1.
Yes, x of s will remain same, just it will be multiplied by e to the power minus 2s. Very good. So in this slide, we have learned about the time shifting. So on the time domain, if we have shifted the time by t naught times, then we can use the time shifting property, which will be e to the power minus st naught into x of s. So for x of t, if it is x of s, for x of t minus t naught, it will be e to the power minus st naught into x of s. So is this clear until time shifting?
Yes, sir.
Okay. Now we'll go to another one, which is time differentiation. So if we have differentiation on the time, so how are we going to convert this into the frequency domain? Okay. So let us say we have x of t in the time domain. And we have x of s. Then if we have differentiation d x of t, differentiation in the time domain, then we have s into x of s minus x of 0. Right? So the transformation is x of s. So we'll have s into x of s minus x of 0. Similarly, if we have d to the power n, if we have nth differentiation by d to the power n, then we'll get s to the power n, s to the power n, x of s minus x dash minus s to the power n minus 1 into x dash of 0 minus s to the power n minus 2 x double dash of 0 minus up to so on minus x to the power n minus 1 of 0. X to the power n minus 1 is the derivative. So all these are derivatives. Okay. These are all derivative terms. X dash, x double dash up to so on x to the power n minus 1 the derivative. So this is also very standard property that we have in Laplace transform. So now cos t. So cos t, there is an already expression that I have given, but let us solve cos t from sin t. So I know that sin t is my x of t, right? Sin t is my x of t, and the Laplace transform is what I already know, which is 1 by s square plus 1. And what is x of 0? Sin 0 is 0. So now what is the differentiation of sin t? Cos t, right? Right? I'm d by dt of sin t, which is equals to my cos t. So now I'm asking the differentiation of this. So from the above expression or the above result, what will be the Laplace transform of cos t? Anyone? So for
S
x of
upon
s upon,
S square plus 1.
S square.
yes, very good. So it is s by s square plus 1, which is also one of the results that we have mentioned before. For cos t, it is s by s square plus 1. So similarly, e to the power minus t, we know we have already solved. So now let us solve e to the power minus t is 1 by s plus 1, which is what we already know. But here, if we calculate x of 0, x of 0 is what? E to the power 0, which is 1. Here it is not 0, so it is 1. Now the differentiation of e to the power minus t is what? Minus of e to the power minus t. So now if we solve this, what will be the expression from here? So s into x of s minus x of 0, right? Hello.
So no idea.
Okay. So e to the power minus t is our x of t. For x of t, it is x of s, which is 1 by s plus 1. So now what I'm saying is d by dt of x of t, which is the derivation of differentiation of e to the power minus t, which is minus of e to the power minus t. So it is fitting in this
minus
second
1
line.
by
Yes, so it is s into x of s minus x of 0. In the previous case, x of 0 is 0, but here x of 0 is 1. So we'll get s into 1 by s plus 1 minus x of 0. So it is s by s plus 1 minus 1, which is minus 1 by s plus 1. We know that for e to the power minus t, if it is 1 by s plus 1, if I multiply by minus 1, it should be minus 1 by s plus 1. But using this property also, I can prove the same. So that's what I have done here, which is s into x of s minus 1. So is this clear?
Yes.
yes.
Okay.
Yes, sir.
Now let me go to another problem. And one more thing, there is less than a minute. So if this meeting ends, kindly join back. We'll continue our discussion. So these are the properties that we are learning by solving a few problems. But once we learn the properties, then we'll dive into the actual problems where we'll be using these properties. Because here I have mentioned which property to be used in which problem for a practice. But when we go into the actual problem, I'll not tell, I'll ask you which property to be used. So there you should be able to correlate which property to be used. Is that clear? If this meeting ends, kindly join back. I think there is less than a minute, so this meeting might end soon. Until then, any doubts?
No, sir.
Okay. Others? So one small mistake that I have made. So here I have made one small mistake. Let me please allow me to correct myself. So this is let me be. So it is s to the power n. After that, we'll have x of 0. So just let me rewrite the expression. I have made small mistake. Minus s to the power n minus 1 x of 0 minus s to the power n minus 2 x dash of 0 up to so on minus x to the power n minus 1 of 0. I have done it in the opposite way. X of 0 I have forgotten, so I have just added that. So these are all the derivatives. Derivatives of x of t at t equals to 0. Okay. So now coming back to our time integration. So again, let us say we have x of t and the differentiation is, sorry, transformation, Laplace transform is x of s. Now if we have integration on x of t, say 0 to t, x of tau, d tau, then we'll have x of s by s. So if we have integration, then it will be by s on the transformation side. So here I have considered very simple two examples. I hope all of you should be able to do this. So if we consider the part one, sine tau, sine t, you know, what is the Laplace transform of sine t? Anyone?
One by s square plus 1.
Very good. 1 by s square plus 1. So what will be the Laplace transform of this integral term?
1 by s square plus tau.
Just check. It is 0 to t x of tau d tau. It is x of s by s. So what is the Laplace transform of this?
1 by s square plus tau by
1 by
S by S square plus tau.
there is no tau in this side. It is just x of s by s. But here it is 0 to t x of tau d tau. So this is our expression 0 to t x of tau, which is sin tau d tau. It is 1 by s square plus 1. So this is our x of s. So now my Laplace transform is x of s by s, right? Getting it, or should I explain in detail?
S by s square plus 1.
Yes, 1 by
1
s
by
into s
s
square
square
plus
plus
1.
1.
Yes, yes. No confusion, right? It is x of s by s because we are integrating this from 0 to t. So it is x of s by s, which is 1 by s into s square plus 1. So if you have any query, please stop me. So these are just using the these properties of the Laplace transform. So what is the Laplace transform of e to the power minus 2t? E to the power 8 is 1 by s minus a. 1 by
S plus 2.
s plus 2. Very good. So now what will be the Laplace transform of integral 0 to t e to the power minus 2 tau d tau?
1 by s into s plus 2.
1 by s into s plus 2. Very good. So this is how we can calculate the Laplace transform of any function that has integral, which is what x of s by s. So this is the time integration. So we have discussed time differentiation, time integration, time scaling, as well as time shifting. 4 on the time side. Now coming to frequency shifting. So if we have a shift in the frequency, how it will be reflected on the time. So we have, say, everything is referred from the x of t. So I'm considering x of t. So we have x of t. It is x of s. So now if I have e to the power, x of s minus a. So if I have x of s minus s naught, or let us say a for our simplicity, x of s minus a. So how it will be reflected on the time? So it is e to the power minus a, e to the power 80, sorry, it is e to the power 80 into x of t. Okay. Whereas if you see time scaling, so if there is time shifting here, there will be minus sign on this e to the power minus st naught. Whereas it is not the case for the frequency shifting. If we have frequency shifting, then we have plus sign on the time side. Just a minute. Yeah. Yeah. We have here frequency shifting, then we'll have plus e to the power 80. Whereas in the case of time shifting, we'll have minus side here on the frequency side. So that is one thing that you should keep in mind. Okay, so now e to the power 2t sin t. So what is the Laplace transform of sin t? Now it is standard. We have 1 by s square plus 1. So now e to the power 2t sin t. So now what will be the Laplace transform of this? It is time shifting. So I'm just keeping this like this. So you see the result and you can let me know.
1 by s minus 1 whole square plus 1.
Why s minus 1?
X of s minus a, sir. Sorry, it
So
is 2, not sir. S minus 2, sorry.
yes, s minus 2. So it is 1 by s
Yes,
minus 2 whole square plus 1. Very good.
yes.
So it is 1 by s minus 2 whole square plus 1. Everyone understood how we got this? Yes, okay. So now we have minus of e to the power minus 3t into t. So I will calculate first what is the Laplace transform of minus t. What is the Laplace transform of minus t? Anyone?
Minus of 1 by s.
Yes, very good. Minus of 1 by s square, right? S to the power n plus 1, right?
Yes, sir.
N factorial by s to the power n plus 1 minus 1 by s square. So now what will be the Laplace transform of this expression then? E to the power minus 3t.
Minus 1 by s
Min-
plus 3 whole square.
Yes, minus 1 by s plus 3. Because it is s minus of minus 3, which is 1 by s plus 3 whole square. So only when the time shifting is there on the time side, we'll have a negative sign in the exponential on the frequency side. Whereas if we have the positive shifting in the on the frequency side, we'll have the same positive expression there. Like if we have t minus t naught, it is e to the power minus s t naught. Whereas if we have s minus a, it is e to the power a t. So this is something that you should keep in mind. So is this clear? Frequency shifting?
Yes, sir.
Yes. So we can kind of correlate this as well as that. Now coming to frequency integration. So similar to time integration, we have say frequency integration. So we have x of t, then we have x of s. So now frequency integration is slightly different. It is s to infinity some x of u du. Okay. In that case, it will be x of t by t. So in the time domain, the integration is from 0 to tau, but whereas in the s frequency domain, the integration is from s to infinite. But it is almost the same. If we have integration on x of t, it is x of s by s. Similarly, if we have integration on the frequency side, it is x of t by t. But the only difference here is what? The only difference here is the integration is from s to infinite. Is that clear? Yeah. So now for solving this, I'll ask a few questions. So let me just write. So slow, step by step we can do. So first I'll ask what is the Laplace transform of sine t. Then I'll ask what is the Laplace transform of integral 0 to t sine tau d tau. Now I'll ask 1 by t integral 0 to t sine tau d tau. Okay. Okay, so what is the Laplace transform of sine t?
1 upon s
1
square plus
upon square
S square
plus
plus 1.
1.
What is the Laplace transform of integral 0 to t sine t d tau?
1 upon s bracket में s square plus 1.
Yes, very good. So this is the time integration property that we have learned. So now if I do 1 by t into integral 0 to t sine tau d tau, now it is coming to frequency integration. So what will be the expression? X of t by t integral s to infinity x of u du, right? So what is the expression here? Anyone? This Laplace transform. So we have x of t by t, right? So what is the Laplace transform? Are you getting it?
No idea, sir.
So
I'll do integration of 1 upon s into bracket s square plus 1.
can you repeat? I'll just check whether what you have said is correct or not.
Integration of 1 upon s into s square plus 1.
Yes, integration. Yes. So basically x of t, we have x of s, right? So x of t by t is integration of s to infinite. So here, this is my x of t now. So x of t by t is what? This is my x of s, right? So here from here to here, just to be clear. So from here to here, I have used time integration. time integration property. And from here to here, I'll be using frequency integration property. Frequency integration. So now we'll have integral s to infinite 1 by s into s square plus 1. I should not say s, I'll say u. 1 by u into u square plus 1 into du. So the integration has to be applied. So now here we have to apply partial fractions and then convert this into 1 by u square plus 1, or we can consider u square to be some k, and then we can do that as well. So we have to apply partial fractions and then simplify this integration. But I'm not going into these details because we have many problems to solve. So here we have to use partial fractions. So I want to cover other concepts, so I'll not be solving this integration. So you have to apply partial fractions and solve this. Okay, so we'll solve a few problems that I have already kept in the upcoming slides where we'll be using partial fractions. So this part I'm currently skipping. Here what we have to do is we have to separate this into each fraction and then integrate that fraction and then solve for the integration. Until this point, it is clear, right? How we got this expression?
Yes, sir.
Okay. So we'll go to our next property. I think this is the final property. So which is frequency differentiation. So we have time differentiation, right? So if it is dx by dt, we have s into x of s minus x of 0. Similarly, if we have x of t, the Laplace transform is x of s. So now what if I have differentiation on the x side? Say if I have dx of s by ds, then it will be minus x of t, or if I put minus here, then it will be x of t. So if you see into t, so if you see the time differentiation, it is all quite similar. So if you go to time differentiation, so if I have derivative, I'll have s into x of s minus x of 0. Whereas here I have t into x of t, but here one minus sign is coming additionally. So we can almost correlate time to frequency, frequency to time, but these minus things are something that we need to pay some attention and should not make any such mistake. So is this clear? For x of t, it is x of s. T into x of t, it is minus d by ds into x of s. So let us solve 1 to 2 problems. Then I think it will be more clear. So for t, so instead of using the direct result, what I will do is I'll use the result for 1. So for 1, input 1, I know the Laplace transform is 1 by s. So for t, what will be the Laplace transform? So basically I'm multiplying by t in the time domain. So what will be there on the right side? Are you getting? Basically, we are multiplying by t. My x of t is 1. So x of t, x of s is 1 by s. So for t into x of t, the Laplace transform is minus d by ds into x of s, right? Agree?
Minus d by ds of 1 by s.
Yes. Very good. So now we have minus d by ds of 1 by s. So what is the result of this?
Minus 1 by s square.
1 by s square. Very good. Yes. So it is 1 by s square. Similarly, t into sine of t. So what is sine of t? Sine t, we know it is 1 by s square plus 1. So now what is t sine t? Anyone? What is the Laplace transform of t into sine t?
Minus d by ds of 1 by s square plus 1.
Yes, very good. So now if we do the differentiation of this, we'll have minus 1 into 1 by minus 1 by s square plus 1 whole square into 2s. So this is my 2s by s square plus 1 whole square. So this is the Laplace transform of t into sine t. So is this clear until this point? Everyone? Okay, I think somebody is mentioned in the chat. Yes, sir. Okay. So these are the things that we have discussed, different types of properties of the Laplace transform. So I'll just briefly discuss about summarize basically. Time scaling, we have x of t, x of s, and x of at 1 by mod a into x of s by a. Similarly, time shifting, if we have x of t, it is x of s, x of t minus t naught, it is e to the power minus s t naught into x of s. For x of t, time differentiation, x of t, if it is x of s, then for dx of t by dt, we have s into x of s minus x of 0. For time integration, if we have x of t, x of s, then 0 to t, x of tau d tau, x of s by s. Similarly, for frequency shifting, if it is x of t, x of s, then e to the power 8 x of t, it is x of s minus a. For frequency integration, if we have x of t, x of s, then x of t by t, we have s to integral s to infinite x of u du. Similarly, for frequency differentiation, if we have x of t as Laplace transform x of s, then for t into x of t, we have minus d by ds of x of s. So now coming to initial value theorem as well as final value theorem. So these are two theorems that we can use to calculate the initial value of the function or the final value. So both are very simple. We have limit x tends to 0, x of t is limit s tending to infinite, s into x of s, and same limit x tending to infinite, x of t will have limit s tending to 0, s into x of s. So only the limits will change. Okay. And again, this is only valid when the limits exist for both x of t as well as x of s. If the limit doesn't exist, then this is not valid. So this is valid only when the limits exist. So the limits should exist. Else it is not valid, of course. The limits should exist for both LHS as well as RHS. Should exist. So now let us quickly solve one problem on each of them. So I have f of s Laplace transform I have given. I am asking limit t tending to 0 x of t. So if I solve problem A, I am asking limit t tending to 0 f of 0, which is limit s tending to infinite s into f of s. So can you tell me what will be the value for this case? So first one is the initial value theorem and second one is the final value theorem.
Infinity, sir.
For the first case.
Yes, sir.
Okay, others agree. So let me just solve. So if we multiply by s, the denominator s will get cancelled. So limit s tending to infinite, we have 2s plus 5 by s plus 2. So in the denominator s and the numerator s get cancelled. So now if I divide by s on the numerator as well as denominator, I will have s. I have 2 plus 5 by s by 1 plus 2 by s. So the idea is whenever we have limits tending to infinite, we have to convert it into 1 by that variable so that that will be tending to 0. So 5 by s will be tending to 0 and 2 by s also will be tending to 0. So now the value is 2. So you should not directly put the limit in the original expression. You should convert into the inverse term so that the inverse term is tending to 0. Then we have to substitute. Is that clear?
Yes, sir.
Yeah. Similarly, second problem, we are asking the final value theorem, which means limit t tending to infinite, f of t is limit s tends to 0, s into f of s. So what will be the value for this case? So I hope others are also following. Is the first problem clear? If it is, please solve the second problem, else you ask me where you have issue, I'll re-explain.
Second one is 4 by 3, sir.
4 by 3, very good. So if I substitute s tending to 0, so first ss will get cancelled. So now we have limit s tends to 0, 4 by s plus 3. So if I substitute s to be 0, then I'll have 4 by 3. So is this clear? Initial value theorem as well as final value theorem. Everyone?
Yes, sir.
What about
Yes,
others?
sir.
Yeah. Okay. So now let us solve few problems. So till now I have given the property and I have asked you how to solve it. So now I'll not give you the property. I'll ask you how to solve. So which property we can use. So we will be now using those properties to solve these problems to find the Laplace transform. After this, we'll do the other way, which is finding the inverse Laplace transform. So for the first problem, from where should we start? So when I say something like this, you can say, sir, we can start from sine t, then we can go to sine 3t, then we can go to e to the power minus 2t. So you tell me from which variable we can start, from which f of t we can start for the first problem.
Sine 3t.
Sine 3t, very good. Sine 3t, what is the Laplace transform of sine 3t?
1
3
upon
by
s
s 3 upon s square plus 9.
Okay, so if this is also somewhat confusing, then what I will do is I'll start from the sine t itself. So if you have any confusion, we'll start from the very basic. So sine t, I know, very standard, 1 by s square plus 1. Now I'm doing time scaling. Which is sine 3t. Sine 3t, time scaling means 1 by 3 into 1 by s by 3 whole square plus 1. So if you solve, we'll get 3 by s square plus 9. So we have used time scaling. Okay. So now what we have? We have multiplied by e to the power minus 2t sine 3t. So now what to do? Anyone? E to the power minus, which property to be used? E to the power minus 2t sine 3t.
Frequency shifting.
Frequency shifting. Very good. So what will be the expression?
Um, 1 by 1 upon no, 3 upon s minus 2 whole square plus 9.
Okay. Is it s minus 2 or s plus 2?
S plus 2, S plus 2.
S plus 2, right? So if we have s minus s naught, or say if we have s minus a, we'll get e to the power at. So if we have e to the power minus at, then we'll have s plus a. So the Laplace transform is 3 by s plus 2 whole square plus 9. So is this clear for everyone how we are using the properties? So now looking at the expression, you should understand which property to be used. So I have started with the very basic expression sine t. So from sin t, I have converted to sin 3t using time scaling. So from sin 3t to e to the power minus 2t sin 3t, I have used frequency shifting. So I have used two different properties and then I got the Laplace transform. So when you use the properties, life becomes simpler because that is already something that people have derived and gotten one property. So now if we use that property, we can bypass the integration. So we need not integrate e to the power minus 2t sin 3t, which is again an iterative series. Instead of that, we are using the results so that we need not perform any integration. Instead, we'll use the results and the existing fundamental equation like Laplace transform of sin t, and then we can get. So is this clear until this point?
Yes, sir. Yes.
Okay. So now for second problem, t minus 1 whole square u of t minus 1. From which expression I can start? See, basically, whenever there is u of t, it means the function is starting from t equals to 0. So that's why u of t minus 1 is given. So second question, from which expression of f of t I can start?
U of t minus.
Okay, u of t minus 1 or just give it a thought. If you are facing any difficulty, then I can explain. But just give it a thought. Just think. Similar problem we have already solved today at the beginning.
From U of t.
U of t, okay. Say we'll start from u of t. What is u of t? 1 by s, right? Okay, then you're right.
Then time shifting, it will be e raised to minus s
Okay,
upon
but
1
here
upon
there is no t square, right, yet. So how do we proceed? So we have started from u of t. Next, which term I have to add before going to t minus 1? T square I have to add, right?
t.
Sorry. I can add t, right? Hello.
Yes, sir. T into
Yeah.
U of t.
T into u of t I can add. Yes, very good. So this is which property?
Time shifting.
This is not time shifting. This is frequency differentiation. Because if I have differentiation on the frequency side, if I go back, if I have differentiation on the frequency side, then I'll get t into x of t, right?
Yes, sir.
Yes. So this is frequency differentiation. So if I differentiate, I'll have minus d by ds into 1 by s, right? Agree?
Yes, sir.
So what is this expression? Mm,
1 upon s square.
1 upon s square. Very good. So now if I again multiply by t, I'll have t square into u of t. But I'll be differentiating the above expression, right? So same thing I'll do, but now I have minus d by ds of 1 by s square. Are you getting? I have added t, then again I have added t because it is t square, right? Is that clear?
Yes, sir.
Others, what about others? I hear it only from one person.
Yes, sir. Yes, sir.
It is clear, right? I have started from u of t, which is very known, 1 by s. Then I have added t, it is frequency differentiation, again frequency
Yes, sir.
differentiation. So two times I'm differentiating. So what will be the Laplace transform? Someone is saying minus 1 by s to the power 4. Okay, what about others? Is that correct?
Minus 1 by s cube.
So basically it is s to the power minus 2, right? So if I differentiate it, I'll get minus 2 by s to the power 3, right? And there is minus 1. So I'll get 2 by s2 by s cube, right? Agree? Because there is one minus before the differentiation. So minus minus will become plus. So it is 2 by s cube.
Yes, sir.
Yes. So now I'll go back. They have asked t minus 1 square u of t minus 1. So how am I going to get that? Which property will I be using?
Time shifting.
Time shifting. Very good. So what will be the Laplace transform of that? So if I have x of t, the Laplace transform is say x of s. So if I have x of t minus t naught, what is the Laplace transform? Maybe I'll go back. I'll not tell you. X of t minus t naught, what is the Laplace transform?
E power s into t naught.
E to the power minus s t naught into x of s, right? So now coming back to our problem, what will be the Laplace transform? Any?
2 into e raised to minus s upon s cube.
Yes, very good. So it is e to the power minus s into t naught. T naught is 1 here. So we'll have 2 into e to the power minus s upon s cube. Okay. Yeah, I think someone has by mistakenly drawn some line. Kindly erase it. So it is 2 into e to the power minus s by s cube. So is this problem clear? So now I here used two different properties, but one property I have used twice. So I have used total 3 properties to get from the basic known expression Laplace transform to the given Laplace given expression. Is this clear for everyone? How we have solved this?
Yes, sir.
Okay. Now let us go to problem number C part, which is f of t is t into e to the power minus 2t cos 3t. So tell me from which part we'll start.
Cos 3.
Cos t, sir.
Cos t. Very good. We can start from cos t. So from cos t, we have to go to cos 3t. So let us start from cos t. So for cos t, what is the Laplace transform?
S upon s square
S upon
s square
s square plus 1. Very good. Now cos 3t. So cos 3t is basically time scaling, right? So we have 1 by 3 into x of s by a, which is s by 3 upon s by 3 whole square plus 1. So if you solve, you will get s by s square plus 9. So this is also like a standard result. Cos omega t is s by s square plus omega square. But if we do not remember, it's okay. If we remember the property, we can derive it on the spot. So that's why I have derived. So here we have used time scaling, right? Everyone agree?
Yes, sir.
Yes. So I got cos 3t. So now what I will do from cos 3t, which term should I add first?
T into cos 3t.
Yes, we can do t into cos 3t, or we can also do e to the power minus 3t, but whatever you say, t into cos 3t. So which property we are using here?
Frequency differentiation.
Yes, very good. Frequency differentiation. So what will be the Laplace transform expression? Like you tell the expression, then we'll derive. What does the property say?
Minus d by ds of s upon s square plus 9.
Yes, very good. Minus d by ds of s upon s square plus 9. So let us, this is also like differentiation of u by v. We can do that. So we'll have minus 1 into v du. V into du is 1 minus u dv, which is s square plus 9. Sorry, minus s into 2s, right? Minus u dv by v square, which is s square plus 9 whole square. So there is less than a minute. If this meeting ends, kindly join back. So if you solve this, I think I will get s square minus 9 upon s square plus 9 whole square. Is this clear, everyone? Just check the calculation. If I have made any mistake, kindly let me know. You also cross check. If this meeting ends, kindly join back. So I have few more problems. I think 5 more slides are there. In the next 40 minutes, we'll be solving few more problems, and we can wind this session after solving the problems. So if this meeting ends, kindly join back. Are you getting this expression? Anyone? Is everyone able to get this expression?
Yes, sir.
Okay. So now what term is left in the question? We have calculated t cos 3t, right? So which term is left now?
E power minus 2t.
E to the power minus 2t. Yes, very good. So now we'll multiply by e to the power minus 2t into t into cos 3t. So which property are we going to use now?
Time shifting.
Time shifting or frequency shifting? So which property will be using now? Frequency shifting, right? Okay. Because frequency shifting will be exponential in terms of time, and time shifting will be exponential in the frequency domain. So what will be the final transfer function? S should be replaced by s plus 2 or s minus 2?
S plus 2.
S plus 2. Yes, very good. So I'll just use a different color for s plus 2. S plus 2 whole square minus 9 by s plus 2 whole square plus 9 whole square. So if you see, we have done step by step. We have started from the known one. Say if you do not remember cos t, then what to do? I can start from sin t. I know the differentiation of sin t is cos t, so I'll use time differentiation. So I'll start from sin t. Time differentiation is s into x of s minus x of 0, which we have already solved. So I can start from sin t, then move to cos t, then move to cos 3t, then move to t into cos 3t, then move to e to the power minus 2t into t into cos 3t. So the expression might look lengthy, but if I know which property to be used, I can start from a known expression and then I can slowly gradually increase using the property. But you should not make any mistake with the minus sign plus sign, else the entire answer will be wrong. So we have to be very thorough with the properties. So that's why I have broken down each property and solved 1 or 2 examples for each property for understanding the property. And then now we are using the properties, and I'm also mentioning which property we have used so that you can correlate how to do. So this is a few Laplace transform examples. If you have any questions, you can stop at this point of time, else we can solve inverse Laplace transform. Should we solve inverse Laplace transform, or do you have any queries?
Yes, sir. Move to inverse Laplace transform.
Someone was saying I'm not able to hear, your audio is very less.
Okay, sir. You will carry on inverse Laplace transform, sir.
Okay, inverse Laplace transform, we'll proceed. Okay, so whenever you see product of multiple expressions in the denominator, what you have to do is apply partial fractions. So first we have to break down 5s plus 7 by s plus 1, s plus 3 into two terms. So we have to perform partial fractions. I hope all of you know partial fractions. If not, let me quickly say. First we have to find the factors of the denominator. Then we can write it is something like a by s plus 1 plus b by s plus 3. We have to calculate a and b. So what I will do is I will combine this a into s plus 3 plus b into s plus 1 by s plus 1 into s plus 3. So now what happens? I'll just write s into a plus b plus 3a plus b by s plus 1 into s plus 3. Now I'll compare the coefficients on the LHS and RHS. That will give me two equations. First equation will give me a plus b is 5. Second equation will give me 3a plus b is 7. So now can you tell me what is the value of a and what is the value of b? Solve these two equations. So basically I have written this in terms of two fractions. So I don't know a and b. So what I have done is I have simplified this into the LHS form so I can compare the coefficients. So what is the value of a? What is the value of b? A is
Equal to 1.
a equal to 1.
Yes.
-1.
B equal to 4.
B equal to 4, right? So every time you calculate a and b, you put it back. So a plus b is 5, 3a plus b is 7. Very good. A is 1, b is 4. So now my Laplace inverse, what is, which Laplace inverse I have to find? I have to find Laplace inverse of 1 by s plus 1 plus 1 by s plus 4. So again, Laplace is linear, so I can break down into 2. So I have Laplace inverse of 1 by s plus 1.
Sir, Laplace inverse of 1 by s plus 1 plus 1 by s plus 3, sir.
Oh, yeah. Thank you. Sorry. Sorry, my bad. Thanks for correcting me. So it is 4 by s plus 3. Yeah. Thank you.
Yes, 4 by.
4 by s plus 3. So now, do you remember Laplace inverse of 1 by s plus 1? Anyone?
Power minus t.
Sorry.
E power of minus t.
Yes. Someone else was also saying the something, right? Vijay Kumar, you are saying, or Pallavi
Yes,
Kumar?
sir. Yes, sir. E power minus t. Same, sir.
E to the power minus t. Yes, very good. So e to the power minus t. And what about the second term?
E to the power -3t.
Yes, very good. 4 into e to the power minus 3t, right? 4 I can bring outside, and 1 by s plus 3 Laplace inverse is e to the power minus 3t. So we know from the like our standard expression, e to the power minus at Laplace transform is 1 by s plus a. So whenever you see 1 by s plus a, it means it is exponential in time domain. So that if you remember, we can solve easily. So this is the first part. So now coming to the second part. So let me just write e to the power minus 2s s by s square plus 4. So inverse also we can do step by step. Laplace inverse of e to the power minus 2s into s by s square plus 4. So from which term should I start? How to solve? Anyone? We can start from the known expressions and we can slowly build. Any clue?
S by s square plus 4.
Yes, s by s square plus 4 is known expression. So we can start from there. So what is the Laplace inverse of s square by, s by s square plus 4?
Sine of 2t.
Sine or cos?
Sine.
Cos of 2t.
Cos 2t,
Cos,
right?
cos.
Sine always has, so always remember cos has s in the numerator, because if you differentiate sine, you will get cos. So when you are differentiating in the time domain, you will get s in the frequency domain. So sine to cos means cos will have s. So that is something we can remember. So now this is my x of s, right? So from here, how to calculate? So now from here to Laplace inverse of e to the power minus 2s into s by s square plus 4. So which property I can use here? Which property? So
Frequency shifting.
frequency shifting or time shifting?
Time shifting.
Time shifting, yes, yes. Yeah, someone was saying. So always remember, if we are shifting time, there will be exponential in the frequency domain. If we have shifting in S domain, then there will be exponential term in the time domain. So now what will be the expression, final expression? Time shift, cos of
2t plus
2 of t minus 2 or plus 2?
plus
T plus 2.
T plus 2.
Okay. Let me just go back. It is minus 2 because it is time shifting, right? So if I have t minus 2, then it will be e to the power minus 2s, right? So this is the thing I was pointing out. Time shifting and frequency shifting, there is a minus change. Similarly, time differentiation and frequency differentiation, there is a minus change. Time integration and frequency integration, there is an integration change. So we have to be very careful. So if I have e to the power minus 2s, then it means it is x of t minus 2, right? I have e to the power minus 2s means x of t minus 2, right? So it is cos of 2 into t minus 2. So which is cos of 2t minus 4. Clear? Everyone?
Yes, sir.
Okay. Any doubts until this point? So
No,
we have
sir.
solved a few Laplace transform. Okay. We have solved few inverse Laplace transform. And there is another important aspect before we move to transfer functions and block diagrams, which is the convolution. So you might have already gone through, but I'll just gone through the lectures, but I'll just please summarize. So if we have any system, say h of t, and say input is u of t, and then say it is y of t, then y of t can be written as x of t convolution h of t.
Sir, U of T convolute H of T.
Sorry. Someone was saying something.
U of T. Sir, input you are defined as U of T, not
Oh,
X.
yeah. Input is u of t, or I should change x of t. Yeah, very good. Thank you for pointing this out. So this is u of t. So this expression can also be written as y of t is equal to integral minus infinite to infinite x of tau, sorry, again, my bad, u of tau into h of t minus tau d tau. So in this way, I can calculate the y of t. But there is also one advantage with the Laplace, because see, convolution means again integral. I have to multiply two time domains. Say one is exponential, one is sine. Then again, I have to apply integration by parts and then integrate from minus infinite to infinite. Again, it is lengthy and complicated. So can Laplace help here? So if I apply Laplace transform, so if you apply Laplace to this, so convolution in time domain will become product in the Laplace domain. So y of t will become y of s, y of t will become y of s, and u of t will become u of s. Convolution will become product. H of t will become h of s. So vice versa. If I have convolution in the s domain, it will be product in the time domain. So now what I will do, I will apply Laplace transform. I will apply y of s equal to u of s into h of s, this condition. Now I will apply inverse Laplace transform. So y of t is equals to Laplace inverse of u of t, sorry, Laplace inverse of u of s into h of s. So you might ask, sir, why we are doing Laplace first and then again inverse Laplace rather than doing one integration? Because sometimes integration can become difficult or complicated, because if you see this expression, we have e to the power minus t and sine t. So if I apply integration, it will be integral minus infinite to infinite e to the power minus tau into sine of t minus tau d tau. So I have to apply integration by parts, and then it is not so straightforward. I have to apply 2 iterations, and then I have to combine and apply integration and then put limits. So a little bit complicated. So instead of this, can I apply Laplace transform property and then calculate? So here I want to find the convolution of f1 of t and f2 of t. So basically I want to calculate f of t, which is f1 of t convolution f2 of t. So now I'll apply the Laplace transform. So f of s is f1 of s into f2 of s. So now if I want f of t, I have to apply inverse Laplace transform. So the expression is f of t is nothing but Laplace inverse of f1 of s into f2 of s, right? So what is f1 of s? Laplace of f1 of t, what is that?
One by s plus 1.
1 by s plus 1, very good. And what about f2 of s?
1 upon s square plus
1 upon s square plus 1, very good. So now I have two such terms, right? So I have to again apply partial fractions. So we need to apply partial fractions because I need to separate. I have two such things, I have to separate it, partial fractions. So always remember, when we have s square plus a square in the denominator, it will correspond to sine term as well as cos term. So we'll get two terms from that. So our partial fractions should consider both of them. So we have 1 by s plus 1 into s square plus 1. So one is 1 by s plus 1, which is very straightforward. So a by s plus 1. Another one is b by s square plus 1, which is corresponding to the sine. Another term is c into s by s square plus 1, which is corresponding to the cos. So now what you have to do is, again you have to do this a into, simplify this, s square plus 1 plus b plus cs into s plus 1 by s plus 1 into s square plus 1. So now you have to solve for ABC. This is very basic math, so I'll not derive the ABC, but I'll use the values of ABC because this you can do later, but I don't want to waste time on solving these three equations. So I have written the ABC values. Let me just take those values and we can use those values. So just give me a moment. Yeah. So A will be half. So you can calculate this later. I'm just using the values. So A will be half. Okay. And B will be half. And C will be minus half. So these are the values that you will get. These small calculation I'm skipping to just save time so we can spend on a useful concept. So now this Laplace inverse of this will be Laplace inverse of a by s plus 1 plus Laplace inverse of b by s square plus 1 plus Laplace inverse of c by s square plus 1, right? So now my f of t is Laplace inverse of half into 1 by s plus 1 plus Laplace inverse of half into 1 by s square plus 1 plus Laplace inverse of minus half into s by s square plus 1. So now can you calculate the inverse Laplace transform of this? Anyone? So what will be my f of t? If I take half common from all of that, if I take half common, what is, so you understood, right? Basically, I have like divided this product into summation. So now Laplace inverse of summation can be individual summation of Laplace inverses. So Laplace inverse of this expression plus Laplace inverse of this expression plus Laplace inverse of this expression. So can you tell me what will be the expression, final expression?
e power minus t
E to the power minus t, very good. plus,
sin t
very good, plus
minus cos t.
minus cos t, yes. So it is minus because there is a minus sign, minus cos t. So this is my f of t. So if you see, we have the only difficulty here is the partial fractions. Other than that, we have not done any complicated calculation or so. We already know the results, so we can quickly calculate only except that partial fractions. Whereas if you do integration, you have to do integration by parts. You have to perform multiple times integration, and that will be a little bit complicated. Here, there is no such complication except partial fractions, which is also easy. I have just skipped for the sake of saving some time. So is this concept clear, how we can use Laplace transform to find the convolution of two signals?
Yes,
Any
sir.
doubts until this point?
No, sir.
Okay. Then we can move to the other concept, which is transfer function. So transfer function is for a system. So we have the same system. Let us consider the same system. So if we consider the same system, so basically transfer function is first of all only for linear time invariant systems. So that I'll mention only for LTI. So for non-linear systems, you can't calculate unless you linearize, only for LTI systems. Okay. So transfer function is defined as the Laplace transform of output by Laplace transform of input. So basically this transfer function, so the transfer function of this is nothing but Laplace transform of output, which is y of s, by Laplace transform of input, which is u of s. And it is here h of s because we know from the convolution. So this is the Laplace transform. Sorry, this is the transfer function. Or you can say transfer function is the Laplace transform or Laplace transform of the impulse response. So Laplace transform of the impulse response of a system. Impulse response means when you excite with an impulse input, what will be the output? That is the impulse response. So if we apply Laplace transform to that, that is the transfer function. Laplace transform of the impulse response of an LTI system is called Laplace transform. Sorry, it's called transfer function, which is also called as TF. I'm just writing it as TF. So what is impulse response? Impulse response means u of t is delta of t. So if u of t is delta of t, then we know that u of s is 1. So if u of s is 1, then what is y of s? Y of s is h of s into u of s. So it is h of s. So if the impulse input is given to a system, the transfer function of the output response, which is y of s, that itself is the transfer function. So this is a definition that people use for defining the transfer function. Is this clear? Just I have just given the definition, nothing much. So now we can solve one problem if the concept is clear. So this transfer function, how it also helps. So now instead of writing things in time domain, I can convert it into everything into frequency domain. So how I can do, let me just quickly write. So now things are like this. So this is my h of s. So I can write into y of s. Input is u of s because my y of s is h of s into u of s. So things are simpler, no convolution, nothing, only product. So I can convert everything into Laplace domain. Then the system can be represented by a transfer function. Okay, now let us solve one more problem. Consider an RL circuit excited by an input voltage V input of S. So everything is in S domain. Let the inductor voltage be VL of S. And the transfer function G of S is defined as VL of S by V in of S. We have to calculate. So I'll give you some insight about how to convert RLC in time domain to frequency domain. So let me consider the element here, element and its voltage. So in time domain here, this is in time domain, this is in frequency domain. Means applying the Laplace transform S domain. So this is the S domain. So to maintain the color, I'll put this in orange. So consider the element R. Okay, I'll use element R. The voltage will be. So now we can back calculate and we can call the element in S domain. Okay, so what I mean, you'll understand once we solve. So voltage in the resistor R for current I is R into I of t. Someone is saying something, your audio is very less.
R into I of t.
Yes, R into I of t. So now if I apply Laplace transform, I will get R into I of S. So if I remove I of S, the element will still remain as R. Whereas in the case of capacitor and inductor, there will be a change. So if you consider capacitor, what is the voltage in a capacitor? I is equals to C dV by dt, right? So if I calculate voltage, it will be 1 by C into integral I dt, right? So now if I apply Laplace transform, it is time integration, which means there will be 1 by S term in the voltage. So I'll have 1 by Cs into I of S. So if I divide by I of S, then the element value is as if it is changed because it is not exactly the same, right? It is 1 by Cs because I am dividing by I of S, right? Say voltage is equals to current transfer function into element transfer function. So element transfer function of resistor is R, whereas for capacitor it is 1 by Cs. Similarly, if we do for inductor, how it is going to change? For inductor, it is L di by dt, right? L into di by dt. So now if we assume a zero initial condition, the transfer function will be S into I of S minus I of 0. Say I of 0 is 0, we'll have S into I of S. So SL into I of S. SL into I of S. So if we divide by I of S, as if the element transfer function is S into L. So if we are dealing with the time domain, the element values are R, C, L, whereas in the case of frequency domain, the element values are R, 1 by Cs into SL. So this is also one standard thing that people follow. So as you move into more circuit-based problems, you will be solving everything in S domain. Same thing, we'll convert it into S domain, solve, and then apply inverse Laplace transform, and we will see that it significantly improves the ease of solving the problems and also significantly reduces the time in solving complicated problems. So in this problem, I have an RL circuit. So I will use R as well as L. Output inductor voltage is VL. Input is V. I have to calculate G of S. So I will be considering a resistor and then an inductor, and the input is V in of S. So everything should be in time domain or frequency domain. So I will be converting everything into frequency domain because time domain, it will be di by dt integral of I dt, whereas in the frequency domain, everything is in product. So this is my V input of S. This is my resistor R. This is my inductor S into L because it has changed. This is my voltage VL of S. So now can you tell me what is VL of S in terms of V in of S? Anyone? What is VL of S in terms of V in of S? Anyone? Hello.
R by 1 plus SL.
Can you please say it louder?
R upon 1 plus S into L.
R by 1 plus S into L. This is like a voltage divider circuit, right? VL is this expression, right? So we have VL of S is equals to SL by R plus SL, right? Just like a voltage divider into V in of S. Agree? Like a voltage divider, resistive voltage divider. So now what was asked? G of S, which is VL of S by Vn of S. So now my G of S is equals to VL of S by Vn of S, which is equals to SL by R plus SL. So this is the transfer function. So is this question also clear? So this is one question I have taken to make you understand regarding the transfer function. So in the transfer function also, basically we'll be using Laplace Laplace domain, means frequency domain. We'll be using Laplace transformation, but how we are going to use and what is transfer function? So for that purpose, I have considered one problem. Is this question clear, everyone?
Yes, sir.
Okay. So now we can go into the next problem, which is block diagram representation. So I think I have to remove the top one. So I'll just block diagram representation. So what happened? Till now we have discussed about the transfer function, right? So any system will be now represented in terms of the transfer function in the S domain. And then we use blocks to do the same. So that's why we call it block diagram representation to represent any system in terms of transfer function as well as blocks. So in this way we can model a system, we can get its time domain expressions. Once we get the time domain expression, we can apply Laplace transform to convert into S domain. Once we get into S domain, we can use this block diagram representation, where if the number of the system is too big, then we can use more number of blocks rather than writing in terms of equation. So it will be pictorially easier to understand, right? We can see how big is system is, and we'll also see how we can reduce the blocks. We can do block reduction, that will be taught in the upcoming weeks. But in this week, for this session, I'll just consider one very simple example. Say I have so this is also called as a negative feedback system, which is also quite popular. I'm considering that. Negative feedback system. So this is very popular, and it will be quite used in our day-to-day life as well. So it will have a summer block. It has an input followed by the transfer function, say g of s, and then this is the output. There is a feedback, and say feedback gain is h of s. So why it is negative feedback? Because this is plus and this is minus, and the input is u of s, output is y of s. So now I need to calculate y of s by u of s in terms of g of s and h of s. So we can do simple, calculation. So if this is y of s, what is this value? What is this value? So if this is this signal is y of s, what will be this value? Pass through h of s. Anyone?
UFS.
Sorry,
UFS.
h of s into y of s, right? Y of s is passed through h of s. So this is y of s into h of s. Agree? Now it is subtracted from u of s. So what is this value?
U of s minus y of s into h of s.
Yes, very good. Now this signal is passed through g of s and the output is y of s. So if I have to write y of s in terms of g of s and the input, what will be the expression? Y of s is equals to what?
U of s minus y of s h of s into g of s.
Yes, very good. So u of s minus y of s h of s is my input, into multiplied by g of s. So now from this I have to calculate y of s by h of s. Sorry, y of s by u of s, my bad. Output by input. Output by input, so u of s. Okay. So now if I quickly calculate this, I will be getting y of s plus y of s, h of s, g of s equal to u of s into g of s. So if I now do simple calculation, I'll get y of s by u of s is nothing but g of s by 1 plus g of s h of s. So this is also a standard a result that we will be using in the upcoming weeks. But as of now, this is just an equation for you, but there are so many things that will go around this expression. How to calculate the stability of the system. There is something called bandwidth of the system. So we'll be applying different theorems like results, I would say. Like how to calculate the write the Bode plot of this, check the stability using Nyquist criteria, check the stability using Rauf-Hurwitz criteria. So there are many things that will go around this system itself, and then this transfer function. But as of now, it is just a transfer function for us, and we have derived using some basic math from the given system. It doesn't mean anything to us because we have not learned about it, but we'll be learning in the upcoming week. So kindly keep this negative feedback system in your mind. We will be discussing it every week in the upcoming weeks till the end. So it is that important. Coming to our last topic, which is the full ordinary differential equations. We can also use Laplace transform to solve differential equations as well. So here I have one differential equation, which is y double dash plus 3 into y dash plus 2y is equals to e to the power minus t. So we can apply Laplace transform. So if I rewrite this expression, it is d square y by dt square plus 3 into dy by dt plus 2 into dy by dt is equal to e to the power minus t. So apply Laplace transform on both the sides.
Sir, it is 2 into y, sir.
Oh, yeah. Sorry.
Yeah.
So many mistakes I have made, and yeah, thank you for correcting every time. 2y is equal to e to the power minus t. So if we apply Laplace transform on both the sides, it is time differentiation result or property that we are going to use, right? So this is time differentiation. So what will be the expression? S square into y of s minus s into y of 0 minus y dash of 0 for the first term. Next we have plus 3 into s into y of s minus y of 0. For the last term we have plus 2 into y of s is equal to what is the Laplace transform of e to the power minus t? 1 by s plus 1. So if I combine and substitute y of 0 and y dash of 0, so y dash of 0 is 0, so this term will directly vanish. So if I combine y of s term, first of all, so we have y of s into s square plus 3s plus 2, and then minus of s into y of 0, which is minus s. So if I take it to the other side, so there is this term that is left, minus s, and then there is this term that is left, which is minus 3. So if I take it that side, it will be s plus 3, right? So this is equals to 1 by s plus 1 plus s plus 3. Agree?
Yes, sir.
So now if you multiply it, we'll have 1 plus s square plus 4s plus 3 by s plus 1. So now if you calculate, you will get y of s is equals to s square plus 4s plus 4 by s plus 1 into s square plus 3s plus 2. Okay. So this is the expression that we got. Now we have to apply inverse Laplace transform. So anyone how to deal with the denominator? Any idea as such? How to deal with the denominator? So we can factorize it, right?
S square plus 3s plus 2 is converted into s plus 1 into s plus 2.
Yes, it is s plus 1 into s plus 2. Very good. Also, there is less than a minute. If this meeting ends, kindly join back. We'll finish this problem before we end this session today. We have s square plus 4s plus 4 by s plus 1, and the other one is s plus 1 into s plus 2. So I'll have s plus 1 whole square into s plus 2. So as I said, we have to apply partial fractions whenever we see such transfer functions. If this meeting ends, kindly join back. So let us apply partial fractions. Okay. So now we need to apply partial fractions and then get into small terms, right? So let us quickly do. And again, I'll not solve for the partial fractions. I'll tell how to do, and then we'll continue with the problem. You can later check whether it is coming or not. S square plus 4s plus 4 by s plus 1 whole square into s plus 2. So if you divide this into partial fractions, you will get multiple terms. So one is s plus 1 by a by s plus 2 plus b by s plus 1 whole square plus c by cs by s plus 1 whole square. Or I could say a plus bs, because it is second order, the numerator will be first order. So b plus cs by s plus 1 whole square. Clear? This is the way we do partial fractions. If the denominator is first order, numerator will be zeroth order. If the denominator is second order, then the numerator will be first order. Clear till this point?
Yes, sir.
Okay. So now if you solve this, you will be getting, sorry, I think my bad. It is second order when like there is no, if the denominator is square term, then we'll have b by s plus 1 and c by s plus 1 square. Or I think both will remain the same. So if the denominator is s square plus say some k1s plus k2s, if it is not factorizable, then you will have in the numerator b plus cs. But if the denominator is s plus 1 whole square, then we'll have b by s plus 1 plus c by s plus 1 square. So after applying partial fractions and then calculating, you will get the terms something like this. Later you can check. So you'll get 1 by s plus 1 plus 1 by s plus 1 square. So this is what I was getting. Because s plus 2 got cancelled. The numerator is s plus 2 whole square. So the numerator got cancelled. Or I'll just quickly solve in another way. So if you write, the numerator is what? S plus 2 whole square by s plus 1 whole square into s plus 2, right? So this is nothing but s plus 2 whole square by s plus 2 is cancelled by s plus 1 whole square. So this I can write it as s plus 1 by s plus 1 whole square plus 1 by s plus 1 whole square. So this is nothing but 1 by s plus 1 plus 1 by s plus 1 whole square. So what is the inverse of 1 by s plus 1? Anyone? So if you apply Laplace inverse, because this is y of s. So now I have to get y of t by applying inverse Laplace transform. So what is Laplace inverse of 1 by s plus 1? Someone saying something? Hello? Laplace inverse of 1 by s plus 1 is e to the power minus t, right? So e to the power minus t plus 1 by s plus 1 square. I can first convert it into 1 by s square, right? Laplace inverse of 1 by s square is what? T. And I have to time shift in the frequency domain, which means there will be exponential term. So it will be e to the power minus t into t. So e to the power minus t into t. So my y of t is 1 plus t into e to the power minus t. So this is the Laplace inverse using frequency shifting. So this is how we solve the linear differential equation, and that's how we get the expression. Is this clear?
Yes, sir.
Okay, if you have any doubts, you can ask. Else, I'll just quickly summarize what we have discussed. We have discussed so many things today, and maybe I have gone a little bit fast to cover the concepts, but I hope you are able to catch up everything and understand all the concepts. So to quickly summarize, we have started with the Laplace transform. Why Laplace transform is needed, what is the motivation, and what is Laplace transform, and we have also understood the region of convergence. Then we have discussed various properties of the Laplace transform, starting with time scaling, and we have also seen a few standard Laplace transform results. We have solved few problems. Then we have understood time shifting property, solved few problems. Then we have discussed about time differentiation property, solved few problems. Then we have learned about the time integration property, solved few problems. Then we have also discussed about the frequency shifting property and solved few problems. Then we have also discussed about frequency integration property and solved a problem. And we have also discussed about frequency differentiation and solved a few problems. So there are so many properties and we have covered all of them. Then we have also discussed about the initial value theorem and final value theorem and solved one problem for each of these properties. Then we have discussed about Laplace transform when the property is not mentioned, how to understand which property to be used, and we have solved three problems. And we have also understood inverse Laplace transform by using partial fractions, as well as how to use the same property, Laplace transform property, and apply inverse Laplace transform based on the expressions. So we have seen which property we have used and we have done the same. Then we have also seen how Laplace transform can help us or make our life simpler in calculating the convolution of a function, and we have solved one problem. Then we have understood what is a transfer function and solved a problem and saw how the elements RLC can be represented in S domain and how we can solve circuit using the S domain. Then we have also understood what is a block diagram and how it is represented, and we have solved a problem. Then we have also seen finally how the Laplace transform can be used to solve a differential equation. So just to mention, both are correct actually. The first method that I have considered and the second, both are same basically. So there is nothing harm in considering that and this. So both should be same, because if you simplify this now, you will get a first order, some first order in S. So it is the same, both can be same. So I was just in a hurry. So this is the overall, instead of B plus CS, I can write some B dash plus C dash. So B dash plus C dash. So it will be the same. So this is what we have discussed in week 2. Just to summarize, we have discussed about Laplace transform, we have discussed about the transfer function, and we have discussed about the block diagram representation. I'll try to upload the video by today itself because the deadline for assignment 2 is, I guess, Wednesday. So if I upload tomorrow, it will be too late. So I'll try to upload by today itself. Please go through the video. If you have any queries, you can reach out to me. So if you have any queries, we can discuss, else we can end this session here. Okay, thank you, Vijay. And if you do not have any queries, we can end this session. It was a nice session. Many people have interacted in this session, and it was quite interactive, and I hope you also got benefited. I wish you all the best for your assignment 2. Again, we'll meet on next Monday with week 3 content. I hope you will do better in assignment 2. Please go through the video and understand if you have any doubts. If you have any doubts, you can comment in the YouTube video, or you can also reach out to me. Okay. Thank you, everyone. Thank you, Vijay. Thank you, Palani Kumar, Niladri, and everyone. Saurabh and Sunil. Thank you so much. Sana, Sultana. Thank you. Good night, everyone. See you on next Monday. and ending this call now then.